Growth models. Exponential growth. If a quantity starts at size p sub 0 and grows by r% written as a decimal r every time period, then the quantity after n time periods can be determined using either of these relations. Recursive form, p sub n equals 1 plus r multiplied by p sub n minus 1. Explicit form, p sub n equals 1 plus r raised to the nth power multiplied by p sub 0, or equivalently, p sub n equals p sub 0 multiplied by 1 plus r raised to the nth power. We call r the growth rate. The term 1 plus r is called the growth multiplier or common ratio. Example 5. Between 2007 and 2008, Olympia, Washington grew almost 3% to a population of 245,000 people. If this growth rate was to continue, what would the population of Olympia be in 2014? As we did before, we first need to define what year will correspond to n equals 0. Since we know the population in 2008, it would make sense to have 2008 correspond to n equals 0, so p sub 0 equals 245,000. The year 2014 would then be n equals 6. We know the growth rate is 3%, giving r equals 0.03. Using the explicit form, p sub 6 equals 1 plus 0.03 raised to the 6th power multiplied by 245,000 equals 1.19405 multiplied by 245,000 equals 292,542.25. The model predicts that in 2014, Olympia would have a population of about 293,000 people. Evaluating exponents on the calculator. To evaluate expressions like 1.03 raised to the 6th power, it will be easier to use a calculator than multiply 1.03 by itself 6 times. Most scientific calculators have a button for exponents. It is typically either labeled like caret, y to the x power, or x to the y power. To evaluate 1.03 raised to the 6th power, we type 1.03 caret 6 or 1.03 y to the x 6. Try it out. You should get an answer around 1.1940523. Example 6. A friend is using the equation p sub n equals 4,600 multiplied by 1.072 raised to the nth power. To predict the annual tuition at a local college, she says the formula is based on years after 2010. What does this equation tell us? In the equation p sub 0 equals 4,600, which is the starting value of the tuition when n equals 0, this tells us that the tuition in 2010 was $4,600. The growth multiplier is 1.072, so the growth rate is 0.072 or 7.2%. This tells us that the tuition is expected to grow by 7.2% each year. Putting this together, we could say that the tuition in 2010 was $4,600 and is expected to grow by 7.2% each year. Example 7. In 1990, the residential energy use in the U.S. was responsible for 962 million metric tons of carbon dioxide emissions. By the year 2000, that number had risen to 1,182 million metric tons. If the emissions grow exponentially and continue at the same rate, what will the emissions grow to by 2050? Similar to before, we will correspond n equals 0 with 1990, as that is the year for the first piece of data we have. That will make p sub 0 equals 962 million metric tons of CO2. In this problem, we are not given the growth rate, but instead are given that p sub 10 equals 1182. When n equals 10, the explicit equation looks like p sub 10 equals 1 plus r raised to the 10th power multiplied by p sub 0. We know the value for p sub 0, so we can put that into the equation. P sub 10 equals 1 plus r raised to the 10th power multiplied by 962. We also know that p sub 10 equals 1182, so substituting that in, we get 1182 equals 1 plus r raised to the 10th power multiplied by 962. We can now solve this equation for the growth rate. R. Start by dividing by 962. 1182 divided by 962 equals 1 plus R raised to the 10th power. Take the 10th root of both sides. The 10th root of 1182 divided by 962 equals 1 plus R. Subtract 1 from both sides. R equals the 10th root of 1182 divided by 962 minus 1 equals 0.0208 equals 2.08%. So if the emissions are growing exponentially, they're growing by about 2.08% per year, we can now predict the emissions in 2050 by finding P sub 60. P sub 60 equals 1 plus 0.0208 raised to the 60th power multiplied by 962 equals 3,308.4 million metric tons of CO2 in 2050. Rounding. As a note on rounding, notice that if we have rounded the growth rate to 2.1%, our calculation for the emissions in 2050 would have been 3,347. Rounding to 2% would have changed our result to 3,156. A very small difference in the growth rates gets magnified greatly in exponential growth. For this reason, it is recommended to round the growth rate as little as possible. If you need to round, keep at least 3 significant digits, numbers after any leading zeros, so 0.4162 could be reasonably rounded to 0.416. A growth rate of 0.001027 could be reasonably rounded to 0.00103. Evaluating roots on the calculator. In the previous example, we had to calculate the 10th root of a number. This is different than taking the basic square root. Many scientific calculators have a button for general roots. It typically is labeled like the nth root, x root, or the y root of x. To evaluate the third root of 8, for example, we type 3 x root of 8 or 8 x root 3, depending on the calculator. Try it on yours to see which to use. You should get an answer of 2. If your calculator does not have a general root button, all is not lost. You can instead use the property of exponents, which states that the nth root of a equals a raised to the 1 divided by nth power. So, to compute the third root of 8, you could use your calculator's exponent key to evaluate 8 raised to the 1/3 power. To do this, type 8 y raised to the x power, parentheses, 1 divided by 3, parentheses. The parentheses tell the calculator to divide 1/3 before doing the exponent. Example 8. Looking back at the last example for the sake of comparison, what would the carbon emissions in 2050 be if the emissions grow linearly at the same rate? Again, we will get n equals 0 correspond with 1990, giving P sub 0 equals 962. To find D, we could take the same approach as earlier, noting that the emissions increased by 220 million metric tons in 10 years, giving a common difference of 22 million metric tons each year. Alternatively, we can use an approach similar to that which we use to find the exponential equation. When n equals 10, the explicit linear equation looks like P sub 10 equals P sub 0 plus 10D. We know the value for P sub 0, so we can put that into the equation. P sub 10 equals 962 plus 10D. Since we know that P sub 10 equals 1182, substituting that in, we get 1182 equals 962 plus 10D. We can now solve this equation for the common difference, D. 1182 minus 962 equals 10D. 220 equals 10D. D equals 22. This tells us that if the emissions are changing linearly, they are growing by 22 million metric tons each year, predicting the emissions in 2050. P sub 60 equals 962 plus 22 multiplied by 60 equals 2,282 million metric tons. You will notice that this number is substantially smaller than the prediction from the exponential growth model. Calculating and plotting more values helps illustrate the differences. So how do we know which growth model to use when working with data? There are two approaches which should be used together whenever possible. 1. Find more than 2 pieces of data, plot the values and look for a trend. Does the data appear to be changing like a line, or do the values appear to be curving upwards? 2. Consider the factors contributing to the data. Are they things you would expect to change linearly or exponentially? For example, in the case of carbon emissions, we could expect that absent other factors, they would be tied closely to population values, which tend to change exponentially. Solving exponentials for time. Logarithms. Earlier, we found that since Olympia, Washington had a population of 245,000 in 2008 and had been growing at a 3% per year rate, the population could be modeled by the equation. P sub n equals 1.0.03 raised to the nth power multiplied by 245,000, or equivalently, P sub n equals 245,000 multiplied by 1.03 raised to the nth power. Using this equation, we were able to predict the population in the future. Suppose we wanted to know when the population of Olympia would reach 400,000. Since we are looking for the year n when the population will be 400,000, we would need to solve the equation. 400,000 equals 245,000 multiplied by 1.03 raised to the nth power. Dividing both sides by 245,000 gives 1.6327 equals 1.03 raised to the nth power. One approach to this problem would be to create a table of values or to use technology to draw a graph to estimate the solution. From the graph, we can estimate that the solution will be around 16 to 17 years after 2008, 2024 to 2025. This is pretty good, but we'd really like to have an algebraic tool to answer this question. To do that, we need to introduce a new function that will undo exponentials, similar to how a square root undoes a square. For exponentials, the function we need is called a logarithm. It is the inverse of the exponential, meaning it undoes the exponential. While there is a whole family of logarithms with different bases, we will focus on the common log, which is based on exponential 10 raised to the x power. Common logarithm. The common logarithm, written log of x, undoes the exponential 10 to the x power. This means log of 10 to the x power equals x, and likewise 10 raised to the log of x equals x. This also means the statement 10 to the a power equals b is equivalent to the statement log of b equals a. Log of x is read as log of x and means the logarithm of the value x. It is important to note that this is not multiplication. The log doesn't mean anything by itself, just like square root doesn't mean anything by itself. It has to be applied to a number. Properties of logs. Exponent property. Log of a raised to the r power equals r log of a. To show why this is true, we offer a proof. Since the logarithm and exponential undo each other, 10 raised to the log a equals a. So a raised to the r power equals 10 raised to log a raised to r, utilizing the exponential rule that states x raised to a raised to the b power equals x raised to the ab power. A raised to the r power equals 10 raised to the log a raised to the r power equals 10 raised to the r log a. So then log of a raised to the r power equals log of 10 raised to the r log a. Again, utilizing the property that the log undoes the exponential on the right side yields the result log of a raised to the r power equals r log a. Solving exponential equations with logarithms. 1. Isolate the exponential. In other words, get it by itself on one side of the equation. This usually involves dividing by a number, multiplying it. 2. Take the log of both sides of the equation. 3. Use the exponent property of logs to rewrite the exponential with the variable exponent multiplying the logarithm. 4. Divide as needed to solve for the variable. Logistic growth. In our basic exponential growth scenario, we had a recursive equation of the form P sub n equals P sub n minus 1 plus R P sub n minus 1. In a confined environment, however, the growth rate may not remain constant. In a lake, for example, there is some maximum sustainable population of fish, also called a carrying capacity. Carrying capacity. The carrying capacity, or maximum sustainable population, is the largest population that an environment can support. For our fish, the carrying capacity is the largest population that the resources in the lake can sustain. If the population in the lake is far below the carrying capacity, then we would expect the population to grow essentially exponentially. However, as the population approaches the carrying capacity, there will be a scarcity of food and space available, and the growth rate will decrease. If the population exceeds the carrying capacity, there won't be enough resources to sustain all the fish, and there will be a negative growth rate, causing the population to decrease back to the carrying capacity. If the carrying capacity was 5,000, the growth rate might vary something like that in a graph shown. Note that this is a linear equation with intercept at 0.1 and slope equals negative 0.1 divided by 5,000. So we could write an equation for this adjusted growth rate as R sub-adjusted equals 0.1 minus 0.1 divided by 5,000 P equals 0.1 multiplied by 1 minus P divided by 5,000. Substituting this into our original exponential growth model for R gives P sub n equals P sub n minus 1 plus 0.1 multiplied by 1 minus P sub n minus 1 divided by 5,000 multiplied by P sub n minus 1. Logistic growth. If a population is growing in a constrained environment with carrying capacity K, an absent constraint would grow exponentially with growth rate R. Then the population behavior can be described by the logistic growth model. P sub n equals P sub n minus 1 plus R multiplied by 1 minus P sub n minus 1 divided by K multiplied by P sub n minus 1.